Okay, now let's go ahead and dive into exploring the assembly instructions available for the Cortex M3. And before I even do that, let me just kind of, for our own sanity here, do a clean and then followed by git status and then maybe git reset minus hard. Yes. So what I did here was reset our uh, foo.s file here to its original state so that I can make changes to that. All right, so now what you have to do is go to this README file again and click on the Cortex-M instructions. Now, if you're not able to click, don't worry, go to the README file and the URL is right here on line 22, right? Okay, so what I'll do is I'll click and it opens up a new page for me. And what I must do now is, right, so just a moment. Let me, yes. Okay. So what we have here then is a page that opens into the online documentation for the ARM Cortex M3. And then within that specifically, it opens this chapter, so to speak, on Cortex-M instructions, right? So these are instructions that can be used in the assembly file. And we'll kind of, pick some instructions from here and try it out by writing an assembly program. Okay, so you can read the details. Let me go ahead and full screen it, but let me walk you through essentially the kind of instructions that ARM provides. So one is for calculations. So uh, so this would mean add, subtract, move, shift. So essentially calculation. The uh, to manipulate or do arithmetic on numbers, right? The other one is data movement related. So data movement would mean, bring it from memory to the CPU register, take it from the CPU register and move it into another CPU register or move it back to the memory, things of those nature. Or sometimes even, shift the current given register to the left and to the right by few positions. So those kind of things. And then there are conditional instructions or condition related instruction, and then there are branching related instructions. So condition related instructions are those that will kind of compare two numbers, see if a zero is formed, a negative number is formed, does the addition overflow, things of those nature are condition related instructions. And then there are branching related instructions, which are more like, hey, if you are executing me, I instruct you to jump to location XYZ. So there are jump instructions, and then within jump instructions, we have kind of conditional and unconditional jumps. So you can just arbitrarily choose to jump to a location, or you can check for certain precondition, like a zero was generated, a negative number was generated or not, and then take a jump. So conditional jump is typically like looping constructs and if else kind of things. And non-conditional branching or jump statements are related to function calls. For example, you kind of executing some program and then you want to jump to certain other location to execute a recipe specified there and then return back. So these are kind of unconditional jump statements. So right, these are the kind of instructions ARM provides then, and then the 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 instructions are given in this table here. It's a pretty long list, and I'm just going to kind of introduce some key instructions, and others you can learn by experimenting, read the documentation on those, and kind of explore and learn. So we have, for example, move related instruction, addition, subtraction, multiply, divide, subtract, compare, these kind of things. And the mnemonic, so to speak, is given here. So now if you wanted to move register to register, you would say move, let's say R1, R2. So that takes R2 and puts it in R1. So the way to read assembly instruction is the leftmost thing equates to the operation performed on right. So here, this is how it is, right? You can also move an immediate value. So I can say move R1, comma, hash 10. So it will take the value 10 and put it here. Now there are limitations on what this number can be. It can be like a 16-bit immediate in this case. So if you wanted to move a bigger number than 16-bit, then you'll need to do something else. And the idea to how do you go about doing that is a different story, which we'll discover as we write our scheduler. Um, but this is essentially then move. You can move between register, move immediate. The immediate into top and bottom. So for example, R1 is 32-bit wide. If you want to move at the bottom 16 bits, then MOV W is what you use, and if you use MOVT, then it moves the 16-bit into the top of the 32-bit register. And this is again a way in which you can, using two move instruction, load the lower and the upper half of a 32-bit number. Then you can kind of move the value of PC, move into PC, move out of PC, those kind of things. Then when we are doing addition, we have so here we see add RD, RN, and an op2. So what op2 means is it can take value of a register, it can take like an immediate number, or it can also take like a label. So, and again here, this is how you read it, right? So RD is the destination register, RN is the source 1, and op2 represents source 2, immediate, or label. So again, these are like the different variants of add, add C, add R, and then essentially what is going to happen is the add to PC, you can add to PC. Add with carry essentially means it will also consider the carry bit in the status flags. So the APSR, long back we had mentioned that there are a few bits at the top here that track the status of the computation. And so whatever the carry bit signifies here, the C bit, that kind of will be included in the addition if we are adding with a carry. It will be included, and also it will be set if a carry is generated, things of those nature. Similarly, we have the subtract instruction, then we have the multiply, the divide, and so on and so forth. Let me go ahead and talk about the compare instruction. So we have, just because this is a useful instruction, so CMP is the compare instruction, and CMN is the negative compare. And what negative means is that the second operand is automatically negated, and then the comparison is performed. So if you're wanting to compare -1 with 1 CMN, what should happen is this should be negated and converted to -1, and then both of them happen to be kind of same, and that's when the comparison result would be set to kind of valid. What I mean here is that the comparison will result in the values being true, or the comparison succeeding. CMP is essentially, -1 with 1 would result in, okay, both the values are not same. And the reason to that is that this is not negated, or the numbers are compared as is. Right. So this is the compare. Then we have the logical instructions, ANDing, exclusive ORing, so on and so forth, and the mnemonic is given here. Then we have shift related instruction, and given a register Rn, the shift is performed on Rn and the value is loaded into Rd. At this point, I should mention that if you're doing something like so, let's say LSI, so I'm saying, hey, take the value of R1, left shifted by 1, and then load it back into R1. So that is also valid. Right? You can use as the destination the same way, the same register that you're going to perform the calculation on. So this then is the shifting related possibilities, right? And then we have rotation related possibilities. Given a register, you can rotate things left, right, with carry, without carry, those kind of things. Then there is something for count, which I have never used. Then there is load related instruction. So this typically means that you would load a register with some value, and that value is in the memory. So load and stored instructions are to get a value from memory, and store is to take a register and put the value of that in the memory. So that is what load and store instructions are for. Various combinations and possibilities available here. I'll just skip through that. I'll just maybe point to the main ones that I tend to use a lot, which is the LDR and the STR. Load into the register and store a register into memory. And the square brackets that you see here, the address will be presented within that, and that would be typically a register and some calculation performed on it, some offset that can be added to it. So that can be presented in the square brackets, but the idea is that the key address from where to load will be provided in Rn. So then you can imagine this is the memory. These are like the registers, R1, R2. So R2, let's say, has 100 stored in it. And when we say LDR R1, R2, and this, there might be like a square bracket here. And what happens is it'll go to the 100th location in the memory and load that value into R1. So the location is specified by R2 as a register. Okay, so similarly then we have store instruction. The store instruction is essentially, hey, take this register and store it in the address specified by the next, right? So here then we have Rn pointing to a memory location, and R1 or Rd in this case is the value that will be pushed into the memory location. So that is the idea. And then, coming to more instructions, the branch related instructions are available here. And the push and pop related instructions are here. Push and pop is something we will use. And this comes in handy during context switching to push certain set of registers on the stack and to pop certain registers from the stack. So this is primarily with respect to stack. Semaphore related things are like, atomic instructions, that when you are executing this instruction, the CPU cannot decide to kind of abort it or cannot decide to abandon it. Or even more importantly, if there are two CPUs, let's say you have 2 and 3 CPUs on a single system trying to reach the same memory, and they go through like the same interconnect or bus matrix, then the semaphore instructions are the ones that will ensure that when one value is getting read, the other CPU doesn't interfere. Or when one value is getting written to the memory and the other CPU wants to write to the same memory, then those transactions are, so to speak, serialized. We can discuss about this much later if we get to it, but do look up exclusive instructions and try to learn more about them. Branching instructions, as I was saying, You can have conditional branch, you can have unconditional branch. Unconditional branch is simply like a B, and conditional branch is like B with the condition name attached to it, and then a label, right? So branch instructions take a label. And what are, conditional branches? So you can, for example, have an instruction which is B and Z, which means branch if not 0. So it checks the status APSR register, and if the 0 flag there is set, then the branch will not happen. But if it is um, right, but sorry, I mentioned it incorrectly. So if the Z bit is set, which is it is 1, so we say that if the result was not a 0, then take a branch. So in this case, the result was 0, hence the flag was set, so the branch will not be taken. Next instruction will be executed. And let's see if we have ABC here and ABC here. If this was 0, so we say branch not 0. Is this 0? Nope, it's not. It's the bit is not set, so the computation did not result in a 0, so this branch must be taken. Branch if not 0. So then it will jump here. So that is the idea of conditional branch. And unconditional branch are taken irrespective of what the computation was. And then these are state change related. For example, SVC is also something we might use, which is supervisory call. It goes from like the thread mode to handler mode. Whenever a thread mode application wants to jump to handler mode and request some service, SVC is what we use. Then there are instructions to enable and disable what do you say the interrupts on the system. And then as we go down, there are instructions to clear set like the bits within a register. So there are instructions related to that. Then there are barrier instructions and some reversing instructions. All right, too many instructions for us. Right. Of course, you don't have to remember all of these. I certainly don't remember. And, there are only few that I tend to remember, which is load, store, move, add, subtract, and branch. These are like the workhorse instructions of any assembly program. And then as you need more functionality, we tend to, revisit the documentation and learn more about the instructions. So now let's go ahead and maybe try out few instructions. So I'm going to take this and put it on another monitor that I have here. Let me restart the code space. Also drink some water. If you're feeling all of this is like a drinking out of the fire hose kind of thing, just stay in the game. It gets easier. Things become very simple. You don't have to memorize everything. Let me just talk about this real quick. So BL is branch and link instruction. So what it does is the dot here represents that we are supposed to jump to the same memory location as the branch instruction. So it'll keep on looping. But the other thing, well, okay, I cannot point it out here, not not yet. Uh, but let's go ahead and try out some instructions. So which instructions do I want to try? We'll try like a move, add, subtract, and branch. So, or maybe even logical instruction. So move instruction we have here. So the hash here denotes an immediate value, and what follows then is a number. If it's a hex number, it's a hex value. If it's just a plain number, it's a decimal value, right? So I'm going to just keep these as is. We do have like move and and then let me also do move R3 or R4 gets R3. Then let me, I don't know, subtract and capture the value in R5 of R4, uh, R1, then maybe, I don't know, left shift something. Let's say I do LSL, logical left shift, that is, and I store the result in R6. I want to move R5 and move by maybe, I don't know, 2, right? So, and then let me specify 2 as like so. So, okay, these are move instructions, and we have add. And actually, how about this? Actually, let me also do subtract R4, R1, R2. So we do add, subtract, then let's remove this, instead make this 5. So we have again a move instruction, then we are doing logical shift, and then let me go ahead and see if I can do a branch. So let me branch to, or how about this? I'll put a label here. I'll label, or rather, let me do Piyush. And what I'll say is, let's, branch to Piyush here. And then after this, let's, branch to, I don't know, Piyush 2. And let me put, this is becoming funny now, but you'll soon understand what's going on here. And hopefully, and let's see, branch to end. Okay, if all goes well, so this program here, let's see what all it has and what all we intend to do here. So first off, reset handler is where we land after all the initialization based on how the CPU boots. Then we move into R1 and R2, 7 and 3, R1, R2. Then we say, hey, you know what? We just want to branch to Piyush. So Piyush as a label is this. So we'll execute R5 equals to R3. So we'll just move value of R3 into R5. But the interesting thing is R3, we haven't done anything with that. So let me move this here so that we have something done with R3. All right, again. So 7 and 3, R1 and R2. Then we say R3 gets 10, which is summation of both of these, which is hex A. Then we say, okay, branch to Piyush. Then R5, we copy the value of R3, so that is 10 or hex A. Then we say, hey, take R5, left shifted by 2 and load this value into R6. And once you've done that, jump back to Piyush 2, in which case we take R4 and then perform a subtraction and put the value value of numerical 4. And then after that, we essentially jump to N. So a lot of moving parts here, but this is what we'll end up achieving. Okay, so let me clear the screen, see if this compiles. Yes, it does, and it has also started QEMU. Let me go ahead and open another terminal, drag and drop it here, and recall that we will do, I think, make GDB. Yes, so GDB has gone ahead and connected with the QEMU session, and so I'm going to put a breakpoint on reset handler, right? And then I do a continue, and well, looks like it just ran away. Uh, ran away to completion. Anyways, the point is here it has reached the end, so our program definitely works. Let me restart this. So quit GDB and then also quit QEMU, and then let me go ahead and let me also actually okay. So so the QEMU is running. Let me start GDB again. All right, what you see here is we are at the instruction, we were at the reset handler already, and that's where when I hit C, it just went ahead and did its own stuff. But anyways, in this run, we are at move R1 7. So R1 should get the value of 7 when I type NI here, which is next instruction. So yes, R1 is loaded with 7. Now we are going to load R2 with 3. So I do NI and it's loaded with 3. Then now we are adding R1 and R2 and then putting the value in R3. So R3 should change. So if we do an NI, then R3 change to hex 10, hex A, which is same as hex 10. Now another interesting thing is the program counter is pointing to this instruction, which is right here. And now what we hope it does is it jumps to Piyush's instruction, and I believe okay, that would be a different address in the future, meaning that would be a little far further away from 9E, wouldn't be 1A0 for sure. So let's do that. When I do NI, the program counter value should change. Yes, it changed to 1A4 opposed to 1A something 0, I suppose. Okay, so now what has happened is it has gone here. We move the value of R3 into R5. R5 is 0 right now. When I do an NI, it loads the value of R3 into R5. Now we are going to do logical left shift by 2 on R5. So what should that become? Well, this nibble here should get modified is what I'm thinking. Let's see. So when I do an I, yes, indeed. So it took A, left shifted it by 2, and it became this. Now, what you can do is you can go ahead and confirm if A shifted to left by 2 becomes this in hex, right? So it has computed this, and now it is going to jump back to Piyush 2. Let me do that. It should be NI. And yes, it has jumped to this location, and this location has this instruction. So now we are going to subtract R1, well, R2 from R1 and then put the result in R4. So R4 is here. I do NI, and if you see 7 minus 3 would be 4. So the 4 is stored in R4, and now it endlessly spins or jumps to the end label where it endlessly spins. Right. So with this, then we have taken a look at the instructions, the possible list of instructions that we have. And again, the link to that is available here, the Cortex-M3 instructions, and this is the URL. You can hit the preview here, and then this is the link that you click. And once you click this, you go to the web page where you have all the instructions. Do try experimenting with those, because one of the things that you need to practice is take a look at the instruction, read the specification or read the usage of that instruction, and then try to use it. Right. And with this, pretty much, we have some idea of what instructions we have, how to go about writing an assembly file, a single assembly file, and also we know things about the fact that instructions are like encoded in a certain way. So all this background information now going forward will become useful when we are trying to use the programmer's model of the CPU and the assembly instructions to create a sort of a scheduler. So with this, then I'll see you in the next one.